So today we are going to speak about elliptic equations. So we know that if we have something like this, where A is the operator of this form, 1D, say A, kg, second derivative with respect to xk and then xg, and the second part of this operator is first derivatives, dxk. A is the matrix obtained by this operation, and D is a domain that is an open connected set. And if we have a solution sigma dt with initial condition 0 x, then if the solution of this equation is good enough, we know that u of x can be represented as a mathematical expectation of the boundary value at the moment when our process hits the boundary. And we imposed some additional condition for this to make sense. We either considered another slightly different equation where we have here something that would introduce an exponential correction with sign that would allow us to consider even unbounded case when this doesn't happen, or we need to guarantee that this is well defined, so this happens. And such additional condition was of the following form, that supremum over all x's inside, don't need here obviously, and tau x is the moment this process psi x of s hits boundary, or infinity if no such s. And one condition that we discussed was as follows. So let's start our lecture with showing that this is not really a restrictive of condition of any kind. So let D be bounded, and coefficients are good enough. For instance, continuous, so this minimum makes sense. This element of this matrix. Obviously, it can be this, etc., by just relabeling. Then holds. So let us introduce the following function with two additional parameters. It is going to be minus y cx1. It's a well-defined function on the whole space, obviously. And these constants are to be determined later. We need both of them because we need two degrees of freedom. Let's apply our operator to this function, which gives us cx1 1/2 a 1x c squared plus b1 of x c. Now this is greater than cy. Oh, that just equals. Let's write it firstly like this: c plus b1 x. Now also assume here that I have a lot of table are continuous. Or just bounded, whatever. Then, since D is bounded, or coefficients are bounded, we can find Y and C such that because this grows to infinity, this controls the growth, etc. I will give you this an exercise. Sorry, I have a crash. I will give this an X. I'm not sharing. I'm not sharing. No, it's back. So I will give this an exercise. It's not really hard. Show it. But the conclusion is that now if we apply the Ito formula to this F with properly chosen coefficients and do this in this form, so T minimum tau x, so this is well-defined stopping time. And this is stopping time because the boundary is a closed set. And we know that the first heating time for a closed set is a stopping time, if it's finite, at least. We get psi x of s ds. And because this holds, we get that this is less than, which immediately allows us to conclude by pushing this into this side that this is now, since D is bounded, this function is bounded. So it's less than 2 means that by the limit of 2, by z for 2 lemma. Just push T small to infinity. So this proof is based on the idea of so-called barriers, also known as Lyapunov function in some contexts. So a barrier, in this case here, is a function that have some controllable in the sense of the original operated behavior inside of the domain here, and typically it has also a proper, in which sense it varies, behavior near the boundary. In our case, we didn't care about the boundary, we care only about the behavior inside of the domain. Such functions are standard tool in the theory of PDEs. They also appear in ergodic theory, they appear in probability. Here, exactly such situations. And it also appears, for instance, in machine learning, in the sense when we have, say, a gradient descent on a bounded parametric set, it want to run just an ordinary gradient descent without caring about the boundary. So we introduce an additional term that gets added to the loss function and that behaves more or less uniformly on inside of this parametric set, but grows to infinity when we approach the boundary. So the gradient descent will try to minimize the loss function. It will naturally not go near the boundary, and we, instead of having to worry about some inequalities, we can just run it on the whole space. It's not something obviously really important to know in modern machine learning, but still. So this is going to be an informal example that kind of pursues pretty much the same route as in what I just said, but in the relation to probability. So let's assume that exists some function one on our domain and satisfying this condition, then at least formally, not caring about like passing to the limit, etc., I can write the Ito formula. In this form, it's also quite often called the Dynkin formula, but Dynkin formula is a slightly more general statement that also involves some martingales. And where tau n is the moment our process, say S, leaves Dn, where Dn is the exhaustion sequence for D. So this sequence of bounded open space such that Dn is included in the interior of Dn plus 1 and their union is exactly D. And now if you apply something like this here, we will end with such behavior less than f of x, something like this. So now if we pass to the limit formally, this is fixed for fixed x. This is by this condition, sorry, is going to grow to infinity, which means at least formally that the moment it hits the boundary, even if it's finite, has infinite mathematical expectation. Now, by developing more refined versions of this argument, one actually proves something like this about even the finiteness of the moment, almost surely, etc., etc. A very good reference here is Friedman's volume 2, stochastic differential equations and applications. So, strictly speaking, finding barriers is kind of a hard task, but if you look through the literature, there are a lot of known already. Now, this propositions that we discussed obviously covered just Brownian motion, which you already know that motion leaves a bounded domain in finite time always. But effectively, it's also true that because of the structure of the barrier, we see that our domain should be only bounded in this direction x1. So for instance, you can discuss such a relation between this solution and Brownian motion in a strip, which is unbounded, but is bounded one direction, which guarantees that this works and your stochastic representation holds. Now, we want to discuss the behavior of our solutions of such elliptic equations near boundaries. For that, we will need to introduce an additional object. Here is a strict inequality. Obviously, it's not going to make any difference unless we start exactly on the boundary. So unless x belongs to the boundary, sigma x is just tau x, defined previously. So we have proposition, stopping time, and the probability that sigma x is 0, even if for points on the boundary, is exactly either 1 or 0. Now, we need to check that this is a stopping time because previously we always defined stopping times with non-strict inequality. So it's slightly different from what we had previously. So we need to introduce some formal argument why it's still true. So first, I will introduce sigma n is going to infinitum. Now t is greater than n minus 1 non-strict inequality when psi x of t doesn't belong to t. These are stopping times. And sigma x less than t is just a union of situation where this happens. And since these ones are stopping times, this belongs to here. So sigma x is a stopping time. Stopping time. Now for second, the argument is pretty much what we already have. You just need to take a standard application. Sigma x less than m minus 1. Now this is union by the previous step. Sigma n less than m minus 1. Now this belongs minus m minus 1, so this belongs to f 0 plus. The right, we take the right continuous version of our filtration, this belongs to its value at 0. But we have the Blumenthal by the Blumenthal 0-1 law, we conclude then, because we established early in our course that this consists only of sets of 0 and a full measure. We already used this very similar argument when we were discussing some stopping times earlier in this course. And now the definition, which was our goal initially, was as follows. The point x on the boundary is called regular if a Wiener diffusion process started at x leaves D, the initial domain, immediately. Otherwise, it is called irregular or singular. It depends on the author, to be honest. And there are two fundamental ideas about regular points. So regularity is actually more or less equivalent to existence of barriers. And the second idea is that if we have a good diffusion and we want to obtain a probabilistic proof, a probabilistic solution to the original Dirichlet problem, we are going to have continuity at the boundary exactly at regular points and only on them. We are not going to discuss the first relation because it's actually more or less of equivalence. People working with PDEs would mostly prefer barriers, talking about barriers. Probabilists may prefer to talk about regular, or it may change, but there is a tendency, at least. Now, we are going to discuss exclusively Brownian motion in what follows. Restrict our attention to Brownian motion. The reason is because you can develop the whole theory more or less in a closed form. So let us recall. We call our function ux f wx tx. So this is the object of our investigation, sorry, phi, and we want to link this to the solution of this Dirichlet problem for at least continuous f and d such that we are in the setting of the previous proposition. So this is well defined, and we also have a we have estimate on the mathematical expectation of this tau x. Now, as we said, regularity is linked to this function being well behaved. That we need some conditions of a point to be regular. And typically what the place where both interpretations agree, whether it's barriers or regularity of points, is that one can propose rather simple geometrical conditions to guarantee that the point is regular. So recall that a truncated cone is the set obtained by rotations and translations of the set. Those points are D, Z, for some vertex, some size, and these are positive, these are RD. So it's just a cone, the ordinary cone, the boundary of the cone. And the proposition we care is let D be greater than 2. It doesn't make sense to consider cones in R1. Just your set D is just an interval. If there exists a cone V with vertex X on the boundary such that V belongs to the complement of D, then X is regular. So let's prove it. Let's start by introducing infinitum those t that Wx of t in V. So for instance, our sigma x is less than this t. Now, for R that obtained by considering this sphere for some R, let me write it. Taking R for this cone, we can cover, one can cover BXR by a finite number W1, W say M of just rotated versions of V. So we have a boundary. This is some cone. And we can just add another here, and we will cover everything around this point, including the interior of D, etc. Now, if we introduce tau k on analogous to this, this is T is Wx of T hits Wk, K from 1 to M, then obviously tau K, because we have Brownian motion, is just distributed as T. Which means that we consider M probabilities that tau equals 0, then it's just the sum of probabilities that tau K equals 0, which is greater than this probability. And this is 1. The probability tau K greater than 0. But what is this probability? Tau K, we defined our vertex, our cones in such a way that the vertex is excluded. This is just a technical assumption, but it allows you to write in this very smooth form. But this minimum tau K greater than 0 K from 1 to M just means that Wx sits at x for positive time. Because if we subtract from this the union on our cones, this is just the vertex. But this is obviously 0. But if it's 0, then probability tau equals 0 is greater than 0 because it's at least 1 over m. But now we can use again the previous proposition to conclude that probability sigma x is equal to 0 is greater than 0, which immediately implies that this is just 1. So the point is regular. Now, instead of this cone condition, one can also consider exterior sphere or exterior ball condition, where instead of touching the boundary by a cone, you consider a boundary that can be touched by a ball. And again, in both cases, you can directly write down a proper barrier. But this is very easy to check. The ball condition is a bit more restrictive. It requires your boundary to be like C1 plus. The Lyapunov boundary is required. This cone condition is very non-restrictive. So for instance, if you consider in D2 something like this, or a cone now is just this object, an infinite triangle, or just a triangle effectively. Obviously, you can touch any part of the boundary with an external cone. So piecewise Lipschitz boundary satisfies this cone condition, etc., etc. And now we are approaching our main result. Before that, we need one additional proposition. So if x on the boundary is regular, then for any positive h, limit when we approach the boundary from inside is 0. Now, let's do it step by step. So the first step can be done by simple methods and by hands, but it doesn't make much sense since it's the argument I'm going to introduce is quite useful in general. So we need the following fact. The following fact. Firstly, we need a definition. A function f is called upper semi-continuous if limit superior when y approaches x is less than f of x for any x. And the fact we effectively need that an non-increasing limit of continuous functions is automatically upper semi-continuous. At least in Ukraine, most courses on analysis never discuss semi-continuous functions, but they're actually quite useful in general. And the claim we want to pursue on the first step is that the function is upper semi-continuous. So to prove this, define the following set of functions. Belongs to D R in ST. The Wiener process started at Y, stays in D, inside of the D, for this interval. Now, it's easy to see that it's continuous function on the closure of D for any S. I will give this an exercise, but generally you just need to recall that D is open and use a dominated convergence theorem. But that's literally all. Now, limit when S goes to 0 from the right of these functions is again, it can be checked by pretty much the same argument I just said, but this is exactly why I'm using T here. I need H everywhere. H. And Fs decrease because the probability becomes less and small and so small. Which, by the fact we formulated, implies that this function for fixed H is indeed upper semi-continuous. As I said, you can actually just use the corresponding statements from analysis and use them directly here by doing those calculations in this specific setting, instead of calling these functions upper semi-continuous, etc. Then we have the following limit superior when this happens is less than, because it's upper semi-continuous, but this is regular point. So sigma x equals 0 immediately. So this is 0. And this is exactly the statement. And now we're ready to effectively formulate let's do another additional proposition maybe. If function again is regular, then for any function that's continuous and bounded on the boundary, we also have this good behavior. When we approach the boundary at point x from inside, x wy tau y. So this is exactly what I meant when said that our initial function u is well behaved at regular points. It's going to be continuous. So let us recall that tau y was infinitum those t, the wy of t didn't belong to D. And step one, let's do it as follows. For any positive R, this limit from inside probability so here our boundary, here our x, here our D, that if we start close to D, we will hit boundary in some proximity of x. So it cannot happen that something like this happens. We go far away from x, even if we started very close to x. To see that, let's fix some epsilon. Then there exists delta 0 greater than 0, such that for all deltas that are less than delta 0, probability maximum W started at 0, I want. The norm, the maximal value of this norm cannot get very high. This is true since almost surely the trajectory is continuous, which means that for any y that now lives inside of D and doesn't go far away from our point x, probability we're interested in is going to be wy t minus y. So this is additional restriction, and we require that it doesn't, we know that it leaves our D in some proximity of x. So here is y, here is x. But now we also put additional conditions that it doesn't even move very far from the starting position. And the idea is now to decompose this analysis to summands. Greater than arrow 2. This is condition A, this is condition B. BA intersect B is greater than P of A minus P of A intersect B complement, and I just remove A by making, so this gets bigger even. But now this is small, so it's greater than minus epsilon by the first condition here for all D less than D0. And by the previous proposition implies the claim. We conclude the proposition before this one implies the claim, because this goes to 1. Now step 2, again, fix epsilon greater than 0 and choose delta such that if y is close to x and in D, is less than epsilon. F is continuous, this is possible. F was defined on the boundary, so we need to have here boundary. Now let's consider wz tau z minus f of x. This is going to be less than tau z minus f of x, indicator that tau hits in a close proximity, plus I will estimate this part, and here's the probability that happens a complement of this. Now, by this, it's less than epsilon probability wz tau z belongs to this, plus probability that this doesn't happen. Now, this is just 1. Epsilon is arbitrary, and this can be estimated by what we obtained here. So this goes to 1 when it hits. So when it doesn't hit, goes to 0. Conclusion. So effectively, we just made rigorous the argument that if we have boundary and we have inner process started near this boundary, near some point of the boundary, it should hit. Regardless of how it behaves, it hits near this point with good probability. So it's a situation where we happen something like this and it hits the boundary of D very far from X are very rare. Not rare enough to make the behavior of this expression as a function problematic. It's actually a sufficient condition also. So not only if the point is regular, then this holds, but also if this holds, the point is necessarily regular. But we are now going to prove it. Now the theorem, which is the conclusion of today's meeting, is as follows. If we have a good function bounded on the boundary of D, then our function u that we defined, let's write it one more time, is such that it solves the Dirichlet problem in the domain. With one important remark that this holds for all regular x. What happens at irregular x is not clear. In general, it means that at irregular points or irregular parts of the boundary, one cannot even define a boundary condition. For instance, sometimes it means that the Wiener process of the diffusion doesn't hit this part of the boundary at all, so this expression never makes sense of this part of the boundary. Now, the cis part is already proven by us, so we just need to check the first part. The argument is classical. So let us introduce, let us take x belonging to the interior of D. Then there exists some R such that Bxr belongs to D because D is open. And now we can introduce tau xr as the infimum of those T that Wiener process leaves the smaller ball. And now we're going to apply the strong Markov property. By the strong Markov property, this is going to be equal the expectation of the conditional expectation of this expression with respect to sigma algebra generated by tau xr, and I always put plus here. This is the sigma algebra generated by a stopping moment. We defined it in the very beginning of our course. And now the strong Markov property applies. It says that the Wiener process started anew at this stopping time. It's again a Wiener process that is independent of the past. So it's just the mathematical expectation of f tau x. So we start anew, but with a random initial condition. So this our new process is independent of this, so we can just integrate here. And because the Wiener process is rotational invariant, when we consider the value of the Wiener process at the moment when it leaves just a ball, an ordinary ball, it's obviously is going to be the integral over sigma is a normalized to integrate to one normalized surface on the boundary is this ball, and the boundary is just a sphere. Now, such functions are the functions that satisfy. Sorry. It's u of y. U of y. This is u of y. And we integrate u of y with respect to this. And functions that satisfy this so-called mean sphere property are known automatically to be harmonic. That is, to satisfy this condition. This is a standard fact. I'm not going to prove it, but again, in the case of the Wiener process, you can prove it by hands. There is a trick to make it easier, but generally speaking, it is contained in every single book on the topic, and it's a well-known thing. So U satisfies the mean sphere property, which means U is harmonic, that is this holds. And this is actually all. I wanted to tell you about the relation between elliptic equations and probabilistic tools. So there is some asymmetry in how asymmetry between probability and PDs. They are not entirely equivalent. Something you get, something you lose. You lose a lot of analytic tools when you go full probability, and you will eventually need those analytic tools in general, but also by using probabilistic arguments, you can describe the boundary behavior of solutions of such equations, and you have more tools on more understanding what is happening. That's all for today, and that's all for the whole course. Does anyone have any questions?
I have a question about the exam.
Yeah, that's
So
we are going to discuss this. Just
okay.
So if nobody has questions, then I will stop this lecture.